Hi everyone, this video is for section 9.5, power series and the ratio test. So I got some questions from some of you because the videos on the website, the posted videos on the website, are a little vague on simplifying. So I'm going to go through a couple of the examples and show you how he simplified these because he did not show all the intermediate steps. Before I do that, I just wanted to quickly look at the notes and let you know just some things that I added to the notes that maybe you might want to. First of all, here I underlined approximated. So a Taylor polynomial is an approximation, whereas a series exactly represents the function. So there's no error between a series and the actual function. A Taylor polynomial is an approximation. So think if I took this Taylor polynomial and I had it go forever, remember the more terms we have, the better it represents the function. So I'm chopping it off. I'm not having it go forever. So it's just an approximation. When I do the series, and remember from 9.1, a series we said was a sum of terms. I'm going to slide my paper up here. Sorry about that. Sum of terms, right? And we use the summation and we went to infinity. So we're not chopping off the polynomial. It's going forever. That's why we can say it's exactly represents. And then down here at the bottom, the definition here, I just wanted to point out that a sub n is a constant. And he says with words that the constant might have a pattern to it or it might not. So it's just a number, it's a constant, and it might have a pattern or it might not. Also, if you are reading the book for this stuff, they use a little different documentation here if you're reading the book. So they use n equals 0 to infinity, and they call the constant c of n, which actually I like better because c is for constant. And then they do x minus a to the n. And so your x value equals a. In this one, my x is c. So that's my center. So this is centered at c. This one, your c is 0 because you have no x minus c. Okay, flipping over. This is what we're getting to next. This is the radius and interval of convergence. So this is just reminding you that a power series is a function. So that depends on x. Okay, so whenever we have a power series, we're going to have an x in there. And what the question that we're trying to answer here is for what values, which I think he says this in words, but I think it's worthwhile writing. For what values of x does the series converge? And he's calling that the domain. This one I just wanted to point out that if you're really thinking about plugging in a 0 here for your center, so you end up with the same number, so this was x minus c. If you plug in the same number, you get a 0 here. Technically, this term would be 0 to the 0 times a sub n, but they just kind of ignore that this 0 to the 0 doesn't really exist. So that's why they go ahead and say, oh, all these terms are going to be 0, and the sum of the series is a sub 0. All right, then they get into talking about the radius of convergence, which is pretty straightforward. I will tell you, if you want to see a nice picture, look in the book on page 68 at the diagram of this function, square root of x. They kind of show the Taylor polynomial representation, and then they show the radius of convergence pretty nicely. So I would take a look at that. Nothing really on this page. This is kind of straightforward. I am not planning on going through example 1 because not really any simplifying happening there. So the next part, which is the biggie of this section, is the ratio test. So think you're just dividing the term after by the term before it. So the way that I remember these, instead of just pure memorization, if the term after is bigger than the term before it, then this is always going to be, so you end up with less than 0. Think of this as approaching 0. Oh, I spelled approaching wrong. Think of that as approaching 0. It's like the geometric, right? It's just like the geometric series. And in the geometric series, we said if r was less than 1, then we diverged. So, and remember, r was a sub n plus 1 over a sub n. So you're kind of checking to see if it is behaving like a geometric series. For this one, this number is bigger than that one, so it's getting big. This is how I think of this. It's getting bigger. We're getting big forever. So it doesn't converge to a number. It just keeps getting bigger, 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 bigger if you're greater than 1 or 0. So then it diverges. If it's getting smaller, 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 approaching 0, think of it as it's converging to 0. And then if it's 1, it's nothing. So just maybe that will help you remember this. Okay, so example 2, 3, 4, 5, 6 is where some of this simplification comes in. And I will go through these problems, maybe in 2 videos. But before then, this is the kind of the gist of the simplifying. I need to turn my camera a little bit here, or not. So take a look at this and see if it makes sense to you. N factorial, maybe start by thinking about a number. 5 factorial is 5 times 4 times 3 times 2 times 1. So we're always multiplying by 1 less than the number. So n factorial can be represented as n times n minus 1 times n minus 2 times n minus 3 forever, right? That's what we're doing here. This is 5 times 5 minus 1 times 5 minus 2 times 5 minus 3. So keep that in mind. N plus 1, take n plus 1 and minus 1 from it. So your first term is going to be n plus 1. Minus 1 from that, you get n. Minus 1 from that, you get n minus 1. Minus 1 from that, you get n minus 2. You can do it with any of these factorials. 2n plus 1 factorial. You start with 2n plus 1. Minus 1 from that, you get 2n. Minus 1 from that, you get 2n minus 1, and so on. So now picture something like, let's see, what shows up a lot in these problems? Picture n factorial divided by n plus 1 factorial. So now just write this out like it's written up here. So this is n times n minus 1 times n minus 2 times n minus 3, so on. N plus 1 is n plus 1 times n minus 1 times n minus 2 times n minus 3, and so on. And then think about simplifying this. You can see these n minus 3's cancel, and everything after them are going to cancel. Not cancel, divide to give you 1. N minus 2, 1's out. N minus 1, 1's out. N, 1's out. So what I'm left with is 1 over n plus 1. So that is the simplifying that he is not showing in these problems. This is the other simplifying that he's not showing. So this is just flashback to Algebra 1, your exponent rules. Common base, multiplying, you add the exponents, you get x plus 5. Picture going backwards. If I have x to the 5th, I could rewrite it as x squared times x to the 3rd. Picture x to the 2n plus 1. So this is a base with exponents added. I could write that as x to the 2n times x to the 1. Right? These are equivalent. So in some of these problems that we're about to look at, they start with this, they rewrite it as this, so then you can simplify further and then you can take the limit. So rewind, put this in your notes if you need to, maybe you don't, maybe that was enough. Now let's look at example 2. So we're determining whether it converges or diverges. So first we want to start with what is a sub n. So that's going to be n, 5 to the n, over 3 to the n plus 1. This part you probably already have in your notes. And a to the n plus 1 is going to be wherever there's an n, turn it into n plus 1. So that becomes n plus 1 times 5 to the n plus 1 times 3 to the n plus 1 plus 1. And then I would go ahead and simplify this further before I do my limit. So this is n plus 1, 5 to the n plus 1 over 3 to the n plus 2. So now your limit is going to be the limit as n, not x. This one doesn't have an x in it. N approaches infinity of this, n plus 1 divided by this. So remember, when we're dividing fractions, we multiply by the reciprocal or the reciprocal. So I have n plus 1 on the top, so that's this, and 3 to the n plus 2. So that's my a to the n plus 1 divided by, I'm going to multiply by the reciprocal. So I'm going to take this and flip it. So 3 to the n plus 1 is going to go on the top. So 3 to the n plus 1 over n times 5 to the n. Okay, so this is what I want to take the limit of. But first, I'm going to do some simplifying. So let's think about rewriting these things. For instance, 5 to the n plus 1, I can rewrite as 5 to the n times 5 to the 1. 3 to the n plus 1, I can rewrite as 3 to the n times 3 to the 1. 3 to the n plus 2 will become 3 to the n times 3 squared. And then you will see some things divide out or 1 out to give you something you can simplify. So the top, n plus 1, I'm just going to leave. The 5 to the n plus 1, I'm going to write as 5 to the n times 5 to the 1. The denominator, I'm going to write as 3 to the n times 3 squared. Right? This is equivalent. Oops, this should be a 2. This is the same as 3 to the n plus 2, which is what I had over on the bottom. Times this, I'm going to write as 3 to the n times 3 to the 1. So 3 to the n times 3 to the 1. And then my denominator, n times 5 to the n, nothing I can really do with that, so that's going to stay. Now, if you look at this, you can start wanting some stuff out. Here's 5 to the n, here's 5 to the n. Here's 3 to the n, here's 3 to the n. 3 to the 1 over 3 to the 2, well, I can take this and call this 3, just plain old 3. So what I am left with is the limit as n approaches infinity. What do I have on the top? 5 times n plus 1. What do I have on the bottom? Looks like a 3 and an n. Okay, now do your limit. These are power 1, so as n approaches infinity, all of this approaches 1, so the limit is 5/3. Remember, on these you don't, technically we should L'Hopital this, right, to prove, but we do not have to L'Hopital these on series problems. So 5 to the 3rd is actually greater than 1. So this is getting bigger and bigger, so this diverges. Okay, so hopefully that helps with the simplifying a little. Let's look at example 3. I'll put the other examples in a different video because maybe you won't need them after this. So some of this I think you probably already have from the first video. So I'm going to start from the limit. I'm not going to write out my a to the n and a to the n plus 1. So this is what I have. This is my n plus 1 times the reciprocal of a to the n. So that's what I have. So first thing I'm going to do is do some rewriting here. Limit as n approaches infinity. So I'm going to write 2 to the n plus 1 as 2 to the n times 2 to the 1. Make this big. And then n plus 1 factorial, I'm going to write that as n plus 1 times n minus 1 dot dot dot. Okay, my second fraction, n factorial, I'm going to write as n times n minus 1 times n minus 2 dot dot dot. 2 to the n is just going to stay 2 to the n. Okay, now look at this and think, what can I simplify? Well, I got 2 to the n divided by 2 to the n, so those one out. Look at your factorials. So n minus 1, n minus 1, n. Anything smaller than it is also going to 1 out because my next term here would be n minus 2. So now this becomes the limit as n approaches infinity of, what do I have left on the top? Just a 2. And what do I have on the bottom? N plus 1. So as n gets bigger and bigger and bigger and the top stays the same, this approaches 0, which is less than 1. It's converging to 0. So this converges. Okay, I will put the other examples in the next video.